Hello everybody, my name is Mariana Cécere. I work in the Institute of Theoretical and Experimental Astronomy and in the Astronomical Observatory of Córdoba. In this opportunity, I'm going to talk about numerical study of MHD modes in coronal loops. This work was performed with Hilario Capitini, Andrea Costa, Gustavo Krause, and Oscar Reula. Through coronal seismology, we can infer the parameters of the coronal plasma. In this case, the oscillation of the coronal loops, the fast sausage mode, and the standard slow mode are the most commonly studied due to their compressibility, which facilitates observations. There are several observational cases that provide information about the properties of the oscillations. For example, Nakariakov et al. 2003 analyzed the oscillation of these coronal loops located between these two zones that are sources of radio and hard X-rays. By analyzing the total source flux, they subtract the background flux to obtain the oscillations on the foot and in the loop top of the coronal loop. They calculate the Fourier transform and they obtain two main characteristic periods. One of them is between 8 to 11 seconds and the other between 14 to 17 seconds. They estimate a coronal loop of this length, this width, this density, this temperature, and this magnetic field, and they conclude that the wave that produces this period must be a fast MHD wave. Also, Inglis et al. 2008, by analyzing this event, they measure a loop length of 40 to 80 megameters. They calculate the Fourier transform and they found a period of 16 seconds in this case. They conclude that the wave that produces this period again must be a fast MHD wave. In both articles, the authors conclude that the oscillations are symmetric on coronal loop. If the deformation of the loop is due to transverse oscillations, we are talking about fast or sausage modes with short periods about 10 seconds. But if the deformation of the loop is due to longitudinal oscillations, we are talking about slow modes with long periods about 100 seconds. In order to study the capability of producing sausage mode, we analyze different energy release scenarios that resemble the action of microflares. For this, we begin with an equilibrium configuration between the coronal loop, the corona, and the chromosphere. We assume a symmetry in azimuthal direction, and we perform 2.5 dimensional simulations. To get an equilibrium between the loop and the corona, these are the profiles to density, temperature, and magnetic fields. As we can see, the loop is denser and hotter than the corona, and the magnetic field is slightly smaller than the corona. We choose these parameters for the longitude, width, density, temperature, and magnetic field. Again, to study the capability of producing sausage modes, we analyze different energy release scenarios that resemble the action of microflares. For example, in a quiet zone, the temperature of a loop is of the order of 1 megakelvin. In this scenario, a typical perturbation will be quickly radiated due to the characteristic radiative time is much smaller than the conduction time. In this scenario, a perturbation located in a small region of the axis could generate an oscillated pattern, which we will call localized perturbation. On the other hand, in an active region, a flare can produce a temperature in the loop base of the order of 10 megakelvin. In this scenario, the conduction time is much smaller than the radiative time, so the loop heats up quickly. This produces a disequilibrium between the loop and the stereo, which we will call a global perturbation. Then, we impose a localized perturbation with an energy that resembles the action of a microflare. In the evolution, we can note that the perturbation is highly collimated by the magnetic field in Z direction. We analyze the density in time for 3 points, we note near the axis the evolution of the propagating shock waves, but at 1.5 and 2.8 megameters, the signal decreases. By performing the Fourier transform, we obtain two main characteristic frequencies. A low frequency equivalent to 100 seconds and related with a slow mode, and a higher frequency equivalent to 13.3 seconds and related with a fast or sausage mode. In this case, the main contribution is due to the slow mode. With the global perturbation, we perform the same analysis by imposing the same energy deposition. In this case, we see that the signal only decreases near the boundary. Again, we perform the Fourier transform and we obtain the same two main characteristic frequencies. A low frequency equivalent to 100 seconds and related with a slow mode, and a higher frequency equivalent to 13.3 seconds and related with a fast or sausage mode. But in this case, the main contribution is due to the fast or sausage mode. Here, we can see more clearly the difference between the two scenarios. With a localized energy deposition, the main contribution to the oscillation is due to the slow mode, while with a global energy deposition, the main contribution to the oscillation is due to the fast or sausage mode. Also, we study different global perturbations. We compare a reference case with two cases. For case 1, the energy deposition is the same, but the same loop has a higher beta parameter. For case 2, the beta parameter is the same, but the energy deposition is higher than the reference case. Here, we see the results. When the energy deposition is the same, but the loop has a higher beta parameter, we see that all values of the amplitude of the Fourier transform increases, and we note in proportion that the slow mode is slightly larger than the reference case. For the case 2, when the beta parameter is the same, but the energy deposition is higher than the reference case, we see that all values of the amplitude of the Fourier transform increases, but in this case, we note in proportion that the slow mode is slightly smaller than the reference case. So, we perform the ratio between the amplitude of the Fourier transform of the density of the fast frequency with respect to the slow one. First, we see in all cases the ratio is larger than 1, that is, the fast mode is the main contribution to the oscillation. For reference case, we obtain 2.7. For case 1, we obtain a smaller ratio because to higher beta parameter, the system is more hydrodynamic and the slow mode starts to become more important. For case 2, the ratio is 5. When the energy of the perturbation is larger, the fast mode contributes more. To finalize, I resume the results in the conclusions. So, from instantaneous energy deposition that emulates a microflare, we distinguish two situations. One of them is a localized energy deposition, and the second one is a global energy deposition that originate coupled oscillations whose characteristic frequencies are two, a slow and fast. In the first case, a slow mode dominates. This type of disturbance excites the propagation of shock waves highly collimated by the magnetic field. In this case, the fast mode have weak signals. In the second case, the fast mode dominates. That is, this type of deposition is able of producing a sausage mode. This suggests that the rarity of this type of mode is due to the requirement that the heat conduction effect must be the dominant, in agreement with loops of active regions. Finally, given global energy deposition, we note that if the deposited energy is the same, but the parameter beta is larger, the fast signal increases by almost the same amount as the slow one. If the parameter beta is the same, but the energy deposited is larger, there is a substantial increase of the fast signal over the increase of the slow one. Well, that is all. Thank you very much for your attention.